네, 오늘 수업 시간에는 챕터 27과 챕터 28, 챕터 제목을 보시면 우리 챕터 26에서 크로마토그래피의 기본적인 이제 원리, 베이직 프린시플에 대해서 다루고 몇 가지 이제 어떤 퍼포먼스 캐릭터리스틱이죠. 어떤 크로마토그래피가 어떠한 성능을 가지고 있는지, 그 성능의 어떤 척도를 나타내주는 몇 가지 요소들, 뭐 플레이트 하이트랄지, 뭐 넘버 오브 플레이트랄지, 뭐 이런 것들, 아니면 리텐션 팩터나 이런 것들에 대해서 다뤘었는데요. 크게 크로마토그래피라고 하면 이제 두 가지 종류가 있습니다. 챕터 27에서 다룰 가스 크로마토그래피, 기체 크로마토그래피죠. 그리고 챕터 28에서 다룰 리퀴드 크로마토그래피, 액체 크로마토그래피. 이 둘 모두 이제 우리 일반적인 실험에서 굉장히 많이 사용을 하고 있는데요. 저 같은 경우도 제 연구에서 이제 가스 크로마토그래피를 사용을 하고 있는데, 그래서 이 두 챕터에서는 뭐 아주 자세한 내용보다는 간단하게 이 두 크로마토그래피가 어떠한 원리를 가지고 있으며, 기본적인 이제 베이스 프린시플은 당연히 이제 챕터 26에서 다뤘던 이제 것과 이제 당연히 동일한데요, 거의. 이제 그러면 이제 이 두 크로마토그래피의 차이가 뭔지, 그리고 여기서 사용되는 어떤 장치가 좀 다를 텐데요. 아무래도 이제 기체를 다루는 것과 액체를 다루는 것과 약간의 차이가 있을 텐데, 그 차이, 그리고 이제 뭐 몇 가지 이제 기본 장치들의 어떤 작동 원리랄지 이런 것들을 그냥 간단하게 소개하는 그런 내용으로 이제 구성이 되어 있습니다. Okay. So chapter 27 is gas chromatography. So in gas chromatography, or we call it GC, in GC, mobile phase is a gas. On the other hand, in LC, liquid chromatography, mobile phase is liquid. Okay. And in GC, stationary phase, on the other hand, it could be anything but a gas. So it could be solid or it could be liquid. Okay. Okay, so I'll just follow the contents of the slide mostly. GC is currently one of the most popular methods for separating and analyzing compounds. It's widely used for separating a variety of compounds, mostly organic compounds. Because GC has very good characteristics such as high resolution, low limits of detection, and it's very fast and it's very accurate and reproducible. Okay? Since the mobile phase of GC is gas, it can be applied for the separation of compounds that is either volatile or that can be converted to volatile, because gas as a mobile phase can only deliver volatile molecules. Okay? So they can be used for the separation of various kinds of molecules, including organic and inorganic compounds. And simple GC system consists of these basic tools, such as gas source, okay? Basically the mobile phase. We need injector of sample, how to inject the sample inside of the instrument. Column, we need a column to separate the mixture by retention, different degree of retention, and we also need detector. Here shows the basic schematic diagram of gas chromatography. Overall general operating principle and mathematical relationships are basically provided in chapter 26. Okay? If you look over briefly the basic components of GC, we first need carrier gas as a mobile phase. Commonly, helium is used. Sometimes nitrogen or hydrogen is also used. So carrier gas is used as at very high pressure, and depending on the type of column, it has different flow rate, and we need to control this flow rate, okay, for the proper operation of GC. Okay? So we need some tools which can control the flow rate, such as flow controller, rotometer, or soap bubble meter. Okay? We have column, which separates the mixture based on the different degree of retention or interaction between two different phases, right? It could be packed or unpacked. We have oven here, so to increase the temperature of the sample, because some sample might not be that volatile, so we need to heat it up to make it volatile. And we have various kinds of detectors for GC. So let's see each one of the basic instruments in more detail. Here shows the injector of the GC. So we need to use the suitable size of sample for better separation of the mixtures. Usually we use micro syringe, something like this. Okay. We usually inject a few or tens of microliter for packed column using this kind of micro syringe. So here shows the syringe, and here shows the injector part. Okay. Overall, inside of this sample port, this part is at least 50 degrees higher than the boiling point of the least volatile compound, so that can vaporize all the components inside of the sample into gas phase. Okay. Here shows the gas sampling valve. So for more quantitative analysis, we need to we need to inject samples in more detail, like in more quantitative ways. So to do that, we use this kind of sampling valve. Okay, here shows the diluent in and out and sample in and out. So by controlling this valve, we can control the amount of injected sample. Okay. So I already mentioned that for GC, mobile phase is gas. We also call it carrier gas. And common carrier gases include helium, mostly helium, sometimes argon, nitrogen, or hydrogen. And the degree of retention is determined by the vapor pressure and volatility of each solute, and also the interaction between mobile phase and stationary phase. Okay. So the choice of carrier gas or mobile phase does not affect the degree of retention. Okay. But they affect the efficiency for the GC system. Okay. If you recall the Van Dimter plot, okay, the plate height is dependent on many different factors, such as multiple path, longitudinal diffusion, mass transfer, something like that. And we had a term which was flow rate of mobile phase, right? Okay. So depending on the type of carrier gas, they affect the plate height. Okay. So depending on the molecular weight of gases, either helium or hydrogen or argon, they affect the diffusion coefficient, and they affect the degree of efficiency in separation. Also, the carrier gas, the kinds of carrier gas affect the stability of column and solutes. Helium or argon or nitrogens are inert gas basically, so they do not really affect the solute or column, but hydrogen or oxygen can react with some functional groups on solute or stationary phase, so they need to be used with care. Okay? They also affect the response of the detector. Okay? Some detectors require a certain carrier gas, such as hydrogen, because some detectors require very high temperature, so they need to make flame. And to make flame with high temperature, we need to use hydrogen gas, something like that. Okay. Actually, the title is wrong. The stationary phase. So stationary phase is very important in GC because that's what separates the different kinds of solute based on the different degree of retention, right? So basically there are three different types of stationary phase used in GC: solid adsorbent, liquid coated on solid supports, and bonded phase supports. Okay. So if stationary phase are solid adsorbents, we call it gas solid chromatography, or GSC. Okay. So the solid material is used as stationary phase and also as support material. So we usually use this kind of material such as alumina, molecular sieve, silica, or active carbon. So for this GSC, since we use solid as stationary phase, it has very long lifetime. Okay? And it can retain and separate the compounds that cannot be separated by other GC methods, such as geometrical isomers on permanent gases. Because stationary phase as solid can retain more, right? Because the interactions are much larger than other stationary phase, such as liquid, right? Okay. But there are also disadvantages, such as there are very strong retention, okay, because of strong interaction with solid stationary phase with the solute, right? Also, there could be catalytic changes on the solute material at the stationary phase, and also this GSC supports this stationary phase has a range of chemical and physical environment that can only be used for a certain range. Okay. When liquid coated on solid supports are used for stationary phase, we call it gas-liquid chromatography. Okay. So stationary phase is a liquid coated on a solid support. Okay. There are many different kinds of liquid stationary phase which are used for GC, okay, including polymers, fluorocarbons, liquid crystal, etc. Many different kinds. And if depending on the polarity or depending on the properties of this liquid stationary phase, we can separate a variety of different kinds of compounds. Okay. So to prepare for this stationary phase or liquid coated on solid support, we usually use slurry of desired liquid phase and solvent. Okay, and we mix it with solid support. Okay, and we evaporate the solvent and coat the liquid phase on a support. Okay, and we pack the resulting material into the column. Okay. The disadvantages of this liquid stationary phase coated on solid support is that liquid could slowly bleed out, like not bleed out, bleed off as a function of time. When after long use, this liquid can be taken out of this solid support because it is just attached, like not chemically attached, just physically adsorbed on this solid support. The interactions are relatively small. Okay. We can also covalently attach stationary phase to the solid support material. So for liquid coated on solid support, the interactions are not that large, right? Because it is just physically adsorbed. But if we can covalently, chemically attach the stationary phase to the solid support, the interactions are really large and they would not bleed off as a function of time, right? So that's how they avoid column bleeding in gas liquid chromatography. Okay. So these chemically bonded stationary phase are prepared usually by reacting the desired phase with the silica surface. So silica surface has basically SiOH group, something like this. So basically the silica surface. Sorry. This silica surface basically have chemical structure, something like this, SiOH. So they can react with the desired phase by chemical reactions. Sometimes they form this kind of bond, SiO-Si bond, or SiCC-Si bond, right? So many different phases, something like this, can be formed by this kind of covalent chemical reaction with solid support. So since they are covalently attached, they are much more stable than the liquid coated on solid support. Okay. So we mentioned about the solid support, liquid coated on support, or covalently attached support. Okay. So there are two main different kinds of support used in GC: packed column or capillary column. So basically, packed column is the tube packed with a certain materials, usually like with have the circular shape. Okay. So we need to make this material, and we need to pack that material into this kind of tube. Okay, that's packed columns, and capillary columns are just open tube. Okay. So depending on the kinds of columns, we need to change the operating conditions for GC, such as flow rate. For example, for packed column, for flow rate are much smaller than the open tubular column because they are packed materials, right? On the other hand, for open tubular columns, we need only very small amount of samples, right? Because there is nothing inside of this tube. It's just open, right? Okay. So depending on the kinds of compounds that need to be separated, we need to use different types of solid stationary phases. Okay. All right. Pushing your way around. As we have learned in chapter 26 that for the best separation and for the best limits of detection, we need to obtain solute with retention factor of 1 to 10 or 2 to 10, right? For good separation. Okay? But the problem is, if there are many different compounds in a mixture, it's not really easy to find one condition that elutes all solute in this good range of retention factor. Okay? So sometimes we need to use gradient elution. Basically, we change condition, we change operating condition as a function of time when we operate GC. Okay? Such as we change color, we change temperature, or we change flow rate, something like that. Okay? Let's see an example. Here shows the two examples for the separation of certain mixture. For this separation, we use just isothermal, just same temperature during the separation of this mixture at 120 degrees C. So as you can see, we cannot really separate these four compounds, right? But when we use gradient elution with different temperatures, we just change temperatures as a function of time, then we could separate all these 9 mixed compounds in a mixture. Okay? So sometimes for better separation, we need to change the operating condition during operation, during the basically as a function of time. Okay? So after you choose a proper mobile phase, stationary phase, column, or operating condition, after you separate it, you need to detect the separated compounds, right? And there are many different types of detectors used for GC, such as thermal conductivity detector, flame ionization detector, nitrogen phosphorus detector, electron capture detector, and mass spectrometer. Okay, so the choice of detector basically depends on the kinds of samples that you need to separate and measure. Okay, so let's see each of these detectors in more detail. Their basic operating principle and how they look. So the first kind, thermal conductivity detector. Basically, as the name indicates, we measure thermal conductivity to detect presence of compound, presence and also the amount of compound. Okay, so this TCD is very universal detector used for GC. Okay. So basic principles are shown in the next slide. So basically it is based on electric circuit, something like this. The details are not that important. Okay. They have some resistors and blah blah blah. Okay. So overall operating principles are shown at the bottom of this slide, as you see. So for this electric circuit, there is current. So there is some constant current is maintained. And if there are a certain materials, either mobile phase or solute, then they basically are in contact with this kind of electric circuit, and they change the thermal conductivity of this circuit. Okay? And to maintain the amount of heat for this electric circuit, we need to change the amount of heat because of this change in thermal conductivity. Okay? And as a result, these resistors temperature and resistance changes, and they can be measured as the difference in voltage. Okay? So basically, we measure the presence and the amount of analytes or mobile phase by measuring the change of thermal conductivity or change of voltage. Okay? To use TCD as detectors, you need to consider several things. First, mobile phase must have very different thermal conductivity than solute being separated. Not then, okay? Because if they have similar thermal conductivity, then we cannot really discriminate them using this TCD detector, right? And for carrier gas, we usually use the hydrogen or helium, because these carrier gases have much different thermal conductivity compared to other common organic compounds. Okay? But the problem of hydrogen is that they can react with metal oxide of the electric circuit. So mostly we use helium gas, okay, for TCD. If you compare the advantages and disadvantages of this TCD, they are really universal detector. They can be used for the detection of many different kinds of compounds. They are non-destructive, so after measuring this the presence and amount of sample, they do not destruct the compounds. Okay. But disadvantages include they detect also mobile phase, right? Because mobile phase mobile phase impurities, because if they have a certain thermal conductivity, they also are very sensitive to change in flow rate, and also they have relatively bad limit of detection. Only they can measure relatively high concentration, okay, much higher than other types of detectors. Next type of detector is called flame ionization detector. So as the name indicates, basically we use flame to ionize the sample. They are also very common type of detector and very universal. Okay, so we make flame by mixing hydrogen and air. So here there are very high temperature flame. Okay, and in the presence of flame, the compounds, the molecules, basically form ions and electrons, right? Okay, and we measure that current. Okay, so they are very universal. Does not respond to common inorganic compounds, because inorganic compounds do not really form ions and electrons. Okay, and mobile phase impurities are not detected. Carrier gas is also not detected. So limit detection and dynamic range are much better than TCD. But the problem is they are destructive, because by this high temperature flame, they basically breaks the compounds into ions and electrons. Okay. Next type of detector is called nitrogen phosphorus detector. So as the name indicates, basically they are really good detector for compounds containing nitrogen or phosphorus. Okay. Basic principles are basically same as FID. They use flame to ionize compounds with nitrogen or phosphorus atoms. Okay, so they measure current. Okay. The advantages include they are very useful for environmental testing or drug analysis, because environmental materials and drugs they usually contain phosphorus or nitrogen. Okay. Since they are especially very sensitive for nitrogen or phosphorus containing compounds, for those compounds they have very good limit of detection. Okay. But also they are also destructive detector, because they use flame. Okay. Next kind of detector is electron capture detector. Okay. For this detector, we use radioactive material with radioactive emitter. Okay. So inside of this detector, we have radioactive material such as nickel 63. They basically emit beta radiation. Beta radiation is electrons, right? So since they make a lot of electrons, we basically have steady stream of electrons. Okay, and we can measure relatively constant current. Okay, but if there are solute, okay, then certain atoms inside of solute capture electrons and reduce the current. And by measuring this reduction, the degree of reduction of current, we can detect the presence of a certain compound. Okay, they are also very useful for environmental testing, especially for compounds with electronegative atoms, because electronegative atoms can capture electrons very easily. Okay. So blah blah blah. Okay. Next kind is atomic emission detector. We have learned about atomic emission, right? So basically, in this detector, there is plasma. Okay. Plasma formed by either by microwave or inductively coupled plasma. Okay. So from the column, we got analytes, and we make plasma, and from this plasma we measure atomic emission. For different kinds of atoms we can detect different wavelengths. Okay? So this atomic emission detector is very element dependent. Okay? Flame photometric detector is special. They are especially very sensitive for compounds with sulfur or phosphorus. Okay? Similar to FID, they also use flame, hydrogen air flame, so we basically decompose analytes, and especially sulfur or phosphorus containing compounds. They form different kinds of excited state molecules, and they give off specific wavelength of light. So by measuring these specific wavelengths of light, we can detect compounds containing sulfur or phosphorus. Lastly, mass spectrometry detector. We also learned about the mass spectrometer, right? So basically here shows the mass analyzer. So we can also detect the mass of the analyte. So by combining GC and mass, we can increase the detectability or sensitivity of the detector. So, for qualitative analysis, we in chapter 26 we learned about the retention factor. Okay, another factor which can be used for qualitative analysis is called retention index, or large capital I. Okay, so this retention index is very simple actually. We denote retention index for normal alkanes, okay, such as butane, pentane, hexane, heptane, something like that. And retention index of alkanes are basically, by definition, 100 times of the number of carbon atoms. So for butane, which have 4 carbon, retention index is 400. For pentane, with 5 carbon, retention index is 500. And this retention index is independent of column packing or temperature or other experimental conditions, especially for normal alkanes. Okay? So we usually compare, we can, by experiment, this retention factor, here in x-axis it shows the number of carbon atoms. Retention factor is basically linear as a function of log of adjusted retention time that has been known already for many tens of years. Okay? So all we can do is for a certain compound, toluene, benzene, or 2,2-dimethyl-butane, we just measure adjusted retention time. For example, adjusted retention time for benzene is here, and since there are already linear relationship between this and this, benzene has this number 6.44, okay, which means that benzene has retention index of 644, something like that. So retention index is a kind of factor which shows which can be used for qualitative analysis. Basically, they can be compared with normal alkanes. Okay? 네, 챕터 28 이제 액체 크로마토그래피죠. 리퀴드 크로마토그래피도 마찬가지로 챕터 27과 마찬가지로 간략하게 그냥 예를 들면 GC하의 차이점, 그리고 어떤 종류가 있는지, 이 LC에 어떤 종류들이 있는지, 그리고 뒤에 보면은 이제 디텍터에 또 역시 여러 가지 종류들이 있는데 간단하게 어떤 종류가 있으면 어떻게 작동하는지. 사실 작동 원리 같은 경우에는 우리가 지금까지 이 수업에서 배웠던 수많은 작동 원리들이 있는데요. UV 빛이랄지 플로러센스랄지 이런 것들을 이용해서 디텍트를 하기 때문에 사실 뭐 크게 여러분들이 다시 배울 내용은 없을 것 같고요. 그래서 간단하게 챕터 28의 내용을 쭉 스킵하면서 넘어가도록 하겠습니다. Okay? So as shown in this slide, liquid chromatography, mobile phase is liquid, right? For gas chromatography, mobile phase is gas. Okay? LC is also very widely used currently. Okay? If you compare LC and GC, the advantages of LC are shown here. Okay? LC can be applied to the separation of any compound that is soluble in liquid. Okay? So they can be more useful for biological compounds or natural polymers or inorganic compounds. Because for GC, if you recall, for GC we need to use GC for volatile or compounds which can be made volatile because mobile phase is gas, but GC can be used for any kinds of material that can be solubilized in liquid phase. Okay? And since mobile phase is liquid, they can be used at much lower temperature than GC. So if if a certain compound is thermally labile, if they are not thermally stable, they cannot be really used for GC. Also, retention of salts in LC depend on their interaction with both mobile phase and stationary phase. So they can be more flexible in optimizing separation condition. Okay, we can change stationary phase or mobile phase. And most LC detectors are non-destructive. We learned about detectors for GC in chapter 26, and some of them, especially if they use flame, they are very destructive. Okay, but LC also have disadvantages compared to GC. Resolutions are much relatively lower than GC. They experience more peak broadening. Okay, because liquid is the gas is much more has much higher diffusion constant and flow rate. So there are many different types of LC, and for different kinds of LC, they use different kinds of stationary and mobile phase. Let's see some of them. So first, for low performance liquid chromatography, for this, we use large, non-rigid support material. So basically, for low, very sorry. Okay. So basically, for low performance liquid chromatography, the support materials have relatively large size, over 40 micrometer. If you recall the characteristics of plate height h, when particle size are smaller, the efficiency of column increases, right? So if particles are really large, the efficiency, the resolution is not that good, right? Since they are low performance, okay? So they are relatively poor system efficiencies and large plate heights. So this low performance LC has relatively broad peaks, poor limits of detection, long separation time, okay? And columns can only tolerate relatively low operating pressure. So the representative example of low performance LC is column chromatography. So we can perform this kind of column chromatography in the lab many times. Okay? We have column. We pack the column with certain material. We usually use like silica or alumina particles. Okay? And we add the mixture, the sample, on top of this packing material. Okay? And usually by just using gravity or by adding external pressure to the top of this column, we can elute the mixture, and by by different degree of retention on these packing materials, we can separate these materials. It's very common technique that we can do in the lab. Okay. On the other end, there is also high performance liquid chromatography, or we call it HPLC. For HPLC, we use much smaller, much uniform, rigid support material. So that's why they are much more efficient than low performance liquid chromatography. Much smaller size. Very good efficiency, small plate heights. Okay. They basically show very narrow peaks, low limit of detection, short separation times, and the columns can tolerate relatively higher operating pressure. So here shows the typical HPLC system. Okay. We usually use solvent reservoirs because sometimes we need to use a mixture of solvent for mobile phase, and we use basically very high operating pressure for HPLC, usually like several hundred ATMs, okay, for packed columns. So because of this high operating pressure, this HPLC system is much more elaborate and much more expensive than low performance LC. Okay. So here shows the basic schematic diagram of HPLC system. Similar to GC, for LC, we can also use gradient dilution for better separation. Okay? By changing the operating condition as a function of time, like the temperature, flow rate, etc. Okay? So here shows an example of gradient dilution of mixture of 30 amino acids. So as you can see, you can clearly see each of these 30 different peaks, right? Alright, so if I summarize, in choosing a mobile phase for LC, several different factors should be considered. Types of stationary phase, such as size of particles, uniformity of particles, for the packing material, solubility of solutes, viscosity, types of detector, purity and miscibility, etc. And especially the selection of a mobile phase can be done by using this kind of table, by checking the properties of each of this kind of solvent, right? Because as you know, this dissolves like solvent which have similar properties to the solute. They can dissolve. Basically, they can have larger interactions with each other. So we need to compare different physical or chemical properties of this solvent or mobile phase. Alright. So there are many different kinds of LC. And here shows the 5 representative LC, which include adsorption chromatography, partition chromatography, ion exchange chromatography, molecular exclusion chromatography, and affinity chromatography. So let's see one by one their basic principle and what are differences between them. So first kind is adsorption chromatography. So basically they separate molecules by adsorption. Okay. So we use solid support, different kinds of solid support have different properties. Some of them are acidic, some are basic, some are nonpolar, and some are nonpolar, acidic, basic, something like that. Depending on these kind of properties, they can retain a certain kinds of compounds, right? If they are acidic, they can be more properly retain the basic compound, right? If they are nonpolar, nonpolar compounds are easily retained, right? They can be more easily used for the separation of nonpolar compounds, right? Okay. So depending on the properties of solid support, each support can be used for different kinds of compounds for the separation. Okay. Next kind of chromatography is partition chromatography. For partition chromatography, we basically use stationary phase as liquid coated on solid support. Okay, so basically separation is done based on their partitioning between liquid mobile phase and liquid stationary phase. So here yellow part is mobile phase, this pink part is stationary phase. So between these two, based on the partitioning of this blue solute between these two phases, we can separate mixture in this partition chromatography. Okay. There are two different kinds of partition chromatography, which are normal phase liquid chromatography and reverse phase liquid chromatography. For normal phase liquid chromatography, stationary phase is polar. Okay, so they can retain polar compounds better, right? Okay. So basically, stationary phase have this kind of support with polar chemical groups, okay, such as cyano, amino, and propylethylene diamine. On the other hand, reverse phase liquid chromatography, stationary phase is nonpolar, so they can be more properly used for the retainment of nonpolar compounds, right? Okay, so depending on the kinds of chromatography, normal phase or reverse phase, they can separate different kinds of compounds, more polar ones, more nonpolar ones. Okay. So for reverse phase, basically we use very nonpolar solid support, either alkyl groups or cyclohexyl or phenyl groups. Next kinds of chromatography is called ion exchange chromatography. So basically they are more properly suited for the separation of ions. Okay. So for this chromatography, for this IEC, the stationary phase has certain ions, either positive or negative. Okay. So if they have positive ions on the solid support, they can separate negative ions. If negative ions are present on the solid support, they can separate positive ions. Okay. So we use different kinds of resins or materials for solid support, and depending on the kinds of support, they can be used for the separation of different kinds of positive or negative ions. Okay. Next kind is affinity chromatography. So basically they separate based on the use of immobilized biological molecules, such as antigen-antibody interactions. Okay, so they are very selective and specific. Okay, if there are antibody molecules on the solid support, they can specifically retain the specific antigen. Okay, like that. So mostly biological molecules, but sometimes they can be used for other types of molecules. Does not necessarily have to be biological molecules. If there are specific interactions between support and solute, they are okay. The last kind is called size exclusion chromatography. Basically for SEC, we use packing material with a certain size of holes. Okay? So if there are mixtures of large and small molecules, as solute travels through the support, small molecules can enter the pores while large molecules cannot. So large molecules flow through the column much faster than small molecules. Small molecules are more retained by these packing materials with small pores. Okay, so basically they separate based on size or molecular weight. Okay. Alright, lastly, similar to GC, for LC also there are many different kinds of detectors. Common detectors include reflective index detector, conductivity detector, UV-based observance detector, electrochemical, and fluorescence detector. Let's briefly look over one by one. For refractive index detector, okay, basically they measure refractive index, the change of light, okay, how much they reflect or bend light. Okay, they are very universal. They are non-destructive because they only use measure of the refractive index. Okay, but the problem is they have a relatively very bad limit of detection. Okay. So here shows the schematic diagram of refractive index detector. So basically, we measure the degree of reflection. Okay. When a certain sample is present, the degree of reflection or bending of light is different, right, compared to solvent-only case. Okay. Next kind is UV-vis observance detector. As you have already learned in molecular spectroscopy, they basically measure UV-vis observance. Okay. If a specific solute observed at specific wavelengths, we can just detect it. Okay. For fluorescence detector, we measure fluorescence. If the solute basically give off a certain fluorescence at specific wavelengths, we can measure it. For conductivity detector, we measure conductivity, especially when we measure ions. Okay, ions basically can generate current, right? So we can change of conductivity if there are a certain analyte. Okay. This is pretty much it. The rest of it you can read the rest of it, and this is the end of chromatography.